Hello people, this is Frank from Muscular Brewing Company. The purpose of this video is to keep spreading my personal and professional thinking about the use of science for independent craft brewing. As a home brewer and potential professional brewer, I follow the philosophy of inspired by nature and crafted by science. Nowadays, I'm making some experiments in my homebrew lab. My objective is to polish my work in the near future. Since my work is heavy in statistics, I decided to put together this video so I can explain you in a simple way the procedure that I use to plan, execute, and analyze my results. So this video is titled Design of Experiment in a Nutshell. But before going there, I need to lay some basic foundation. A mathematical equation is a way to determine the relationship between variables and a response of interest. There are mathematical equations that are deterministic, meaning that no matter the combination of numbers and the corresponding mathematical operator, you will get the same results all the time, such as 2 plus 2 is 4, 4 times 4 is 16, and 6 plus 4 is 10. Now, this led to a basic mathematical equation that allow you to predict in advance the result without the need to write it down on a piece of paper, such as A plus B equals C. Now, using the A plus B equals C, that is a basic mathematical equation, you can use any number and predict the result in advance. In this case, it's going to be C. Such as 2 plus 2 equals 4 or 1 plus 1 equals 2. On the other hand, there are probabilistic equations which allow you to evaluate the probability that a combination of variables will deliver a response of interest, like probability of C equals A plus B. Why we need probability? Well, because of the natural variation that surround us, also known as background noise. This is the meaning of our life. Variation is the essence of our existence. Different beers, different hops, different yeast, different grains, water profile, color, cars, food, whatever. So variability keep us moving forward, right? Despite the blessing of variability is an obstacle when people like me try to characterize and predict natural phenomena and use it to improve our life, like making a great beer. So the only tool to evaluate this variability is statistics. Statistics help to determine what is the natural variability in a response, aka background noise. This would allow us to increase the resolution and see the response of interest. As a comparison, imagine that you are in a brewery having a few beers with a friend. There's a lot of people also having a beer and talking to other people, right? So the only way you can talk to your friend and exchange information, it is in two ways. First, if you tell the people to shut up, or simply if you increase the pitch of your voice in order to be above the background noise. And then there is the only way that you can talk to your friend and keep having beer. Okay? So the bottom line is that you have to find a way to bring the information exchange above the background noise or the chatting of the other people. So the data is exactly the same. There is also natural background noise, and you can find a way to reduce this background noise that sometimes is doable, not to 100%, but it's possible. And or you can increase the pitch of your response, so you will be able to see it and perform characterization. Okay, so this is the only way that you can increase the resolution and see your response of interest. One of the multiple tools used is called factorial experimental designs. You select the variables and the response of interest and evaluate the correlation, if any. Using a statistical software, you plan the experiment, execute, and analyze and determine a probability equation. And this is a better approach than trial and error, as I plan to explain you at the end of this video. So in the next slides, I will explain in a nutshell what design of experiments are all about. So in this example, you have this black screen here. This black screen is called the experimental space. So you have two variables. You have the level of sulfate in per ppms, and you have the boiling time in minutes for making a what? An IPA, an Indian Pale Ale. So your objective, your response is going to be the best flavor and bitterness profile that you can get. So in the beginning, before doing anything, you're blind. You're black out like this experimental space because you don't know the correlation between these two variables and the response of interest. Now imagine that you are in a cave. You're completely blind, black out. You have a flashlight in your hand. So what is going to be your reaction? You're going to take the flashlight and you're going to start putting it in different places around the cave until finally you find a way out. You put your flashlight in a door or in an exit, and once you do that, you walk to the door and you go out and go to the light, right? You find a way out. Experimental designs are the same. Experimental designs are going to be your flashlight that is going to allow you to examine what is going on in this black screen. So what you do is that you randomly select a place inside this big experimental space and set up experimental design that is represented by a square. Okay, and this turned out to be a sub-design space because it's a tiny design space inside the big design space here, the black screen. So now, the flashlight is not on yet. So before going there, as you can see here, there are 4 corners. So each corner is an experiment. For example, in this left side, you have short-term boiling time, and you're modifying the level of sulfate. So you have a high level here and a low level here. If you go to the right, you have a high level of boiling and the same level of sulfate. So you keep going like that, and once you have all the 4 trials performed, or beer in this case, what you do is that you taste them and you rate them. And this rate, you plug it into the software, and the software is going to build for you a probabilistic mathematical model. And then you shed light. So what is going to happen, you're going to analyze this preliminary area and where you have a little bit of light here. And you can see here that is some correlation between the variables and the response. But I am not really close yet. How I know? Because you look into the maximum flavor profile and bitterness of your beer. Okay, imagine that you are in the bottom of a tall mountain and you're looking up to the hill, to the peak, because you want to maximize your response. So here's the same way. Here I see like I'm slightly on the bottom. Now, the good thing about experimental design is that instead of going back and randomly start looking around, poking around different places around here, this mathematical model is going to allow you to predict where is the spot inside this experimental space that you are going to have the higher probability of finding what you're looking for. And what you do is that you use what is called the method of steep ascent. That is basically a linear model that forecast out of this small experimental space. It's telling you that here is the place that most probably you're going to find what you're looking for. So you set up your flashlight again. Another DOE. You execute your trials the same way that you did it previously, different levels, going down a lot. And then once you plug in the results into the software, you shed light. So if you can see here, I see that I'm really close to the peak. I'm seeing some round oval behavior here, response in function of the sulfate and the boiling time. Okay, and this roundage response in statistical terms is called concavity. Now, because you have concavity, you're going to be unable to model it because you only have 4 trials. So what you do is that you use what is called response surface methodologies in order to increase the number of trials and be able to have enough uh, experiments in order to model the response. And this is a central composite design that is beyond the scope of this presentation. So once you execute this, what you do is that you have the entire map of the peak of the mountain. So it's telling you here that this is the most probable spot that you can find the best flavor and bitterness profile of your beer. So once you do that, you go down and extrapolate. You say, yeah, I need this boiling time. And then you extrapolate to the sulfate level. Say, yeah, I need this sulfate level. So once you have that, you can see here that you have shed light to the entire map. Okay, so now going back to the trial and error. This is a very interesting map because if you eyeball here, it's telling you that if this is the area, you can find most probably find your maximum bitterness and flavor profile of your IPA. This is about probably, I will say, 10% of the entire map. So this is telling you that you have a 90% probability of failure if you do trial and error. Okay, so if you go here, you're probably going to fail. If you go here, you're probably going to fail. You go here, you're going to fail. So you have 90% probability of failure. So this mathematical model has have increased the probability of success in 90%. So this is the real power of experimental science. It's allow you to save time and money by increasing the probability of success. And you can go around here in this purple oval thing and you can play around and say, yeah, I want to go a little bit to the left, right in this case, a little bit to the left. But also it's telling you, no, I'm not going to check here. I ain't going to check here. I ain't going to check here. Why? Because you're going to waste your time and your money. So this is what experimental design is all about. I say thank you for watching my video, and if you have any questions or comments, just drop me a line. Thank you again, and cheers.